Hello, ladies and gentlemen. Welcome to our next lecture from Data Analytics course. Today we will be covering, we continue coverage of probabilistic computation methods. We will finish what was started on Friday's lecture, and if any time allows, and we'll have still power to work, we will move to Markov chain Monte Carlo methods. So just to be clear, what we've started are we discussed finished our discussion on pseudo-random number generators, and we've discussed how it's generally realized. The main idea is the so-called Mersenne, most popular current algorithm is so-called Mersenne twister, and this algorithm is implemented in most of programming languages. Having good pseudo-random generator, we can use it to generate samples from probabilistic distributions in order to have proper sampling procedures and estimate expected values of quantities we are interested in. I've mentioned that while the random number generator, for example, congruent generators or any other generators, work on the base of generating natural numbers, or generally numbers between 0 and 1, in the interval 0 and 1, which comes from natural numbers as just by a scaling factor, and generally that gives us uniform probability distribution on given interval, usually 0, 1. And in order to convert that to any other practical distribution, we need something which is called quantile function. And quantile function is strongly related to continuous to cumulative distribution function, which is, if you remember, an integral of probability density function, or otherwise a function that comes to each element of probabilistic set X assigns a value between 0 and 1, and formally it means that it assigns to an X a probability of an indicator function of a set between minimal value of X and X. In case of single variable functions, it's obvious. In case of one variable, it's rather obvious. In the multiple variables, it's more complicated. Either way, quantile function for our intents and purposes is the inverse of CDF. So the function that will take a number between 0 and 1 and assign it a value of X from the probability space. And that actually is a very good option when we want to go from uniform random numbers into into a given probability distribution, at least in one dimension. Because if we get a uniformly distributed numbers between 0 and 1, then a sequence of values from of quantile function computed at each of those values between 0 and 1 will be a sequence, will be a sample from our desired distribution for which the quantile function is defined for. So this is a very option. So inverting the cumulative distribution function, we can easily compute the any kind of random number that comes from that comes from our distribution. So we can sample from our distribution. This is of course not only option. A very simple option also in one dimension is grid approximation, which is a very simple way of approximating our probability density function with a certain probability mass function, really. And the idea is that we define a grid on on the probabilities, on the values, on the vector probability space, and we compute the value of the of our density of interest. In case of Bayesian computation, we compute the value of the prior at each point of the grid, we compute the likelihood at each point of the grid, we multiply the prior and likelihood, and we standardize the posterior by dividing each value by the sum of all values. And then we can sample from grid like from a discrete distribution, which is very simple, because sampling from discrete distribution is trivial in the case of just getting proper value from given interval, because this is a probability mass function. So getting it has only finite number of values, and sampling from finite number of values is trivial. And now we'll do some examples of sampling, so you could see what actually happens with samples when we take values from a distribution. Because the fact that we can get samples from given distribution allows us to compute certain statistics that we are interested in. We've mentioned before expectation histograms, etc. And those values will be, having those values, we'll be able to analyze the function, the probability distribution behavior, for example, computing values of interest. And as we can see, the main idea of probability density of sampling is that increasing number of samples from the distribution, as we've mentioned about central limit theorem, we get the better and better estimates of given expectation. As you possibly remember from our lecture, average of samples of function values taken from a certain distribution will give us the expected value of that function over this distribution. So sampling from one distribution we will get the values of so-called Monte Carlo estimator. So now average of those samples will be a Monte Carlo estimator of the given expected value. And this estimator, as we mentioned before, is covered by a Monte Carlo standard error, which comes directly from the central limit theorem. If we take the histogram, we can observe how histograms behave. If here we consider the histogram normalized to given bin probabilities. So this is a histogram that can be treated as a probability mass function defined over intervals of the variable x. And as we can see, sampling from our distribution, we get a histogram, the number of counts divided by total number of samples, so the probability of each of the for each of those, we have defined the Monte Carlo standard error. And this Monte Carlo standard error comes from the same situation as we mentioned before. We compute the expectation of each of those indicator functions. And because the expectation is an average, so it's a sum of samples taken from the same distribution, it covers under the central limit theorem, and central limit theorem in this case gives us the standard deviation or Monte Carlo standard error, in precise, of each of those estimates. So this is our estimate of this normal density that we've discussed here, the normal density with a mean at 1 and the standard deviation of 1.125. If we take an analytical rescaled probability density function, we will get the following. We will get the following distribution. So you can easily see that it well fits within the errors given. Of course, with certain disturbances coming from that. This is still a sampling procedure. Depending on the binning, we will have some issues. First of all, if you remember from the lecture, the thinner the interval, the lower probability the event, the higher uncertainty we have with given number of samples. So, if we take very fine bins, we will have first of all a lot of noise in our histogram, and we will have very large uncertainty because each of those events does not have enough samples to provide certainty about its behavior. If we take a little number of bins, then we have a lower uncertainty, but we have worse representation of our probability distribution. In case of some kind of middle ground, we have to tackle both of those things. More uncertainty, perhaps the better shape representation. So a proper choice of binning not only changes the visual aspect of histogram, which you already know from basic data analytics courses, but also it changes the actual uncertainty about our probability density, probability distribution that is underlying in the under the problem that we are interested in. As a companion of histogram, as I mentioned, is an empirical cumulative distribution function. ECDF has the property that it's assigns the probabilities from extreme to extreme values that were measured. So it kind of estimates our probability density, cumulative density function of our distribution. What we can see here is that the typical part of the ECDF is that uncertainty of ECDF is highest in the middle because the probability of going below the extreme values is always 0, and going above maximum value is also always 0 in this context. And depending when we are inside, all those estimates come from the uncertainty of the interval from here to here. So depending on the interval, those values will change. This was a simple situation because for normal distribution we generally can do everything analytically. Analytical computation in normal distribution is easy. That's why normal distribution was so popular in all kind of statistical applications that were covered over the ages. However, not always we have such situation. Even a simple variable transformation require very difficult analytical computation to get to somewhere we want to. So, for example, transforming the normal value, value samples from normal distribution through inverse log it. So the classical problem of transforming from real to numbers to 0, 1 interval, of course, causes the situation that while original values before transformation, real numbers, had a normal distribution, the transformed variables within 0 and 1 interval, of course, will not have. They will have a transformed distribution. And that transformed distribution will require analytical computation. However, this is not a problem if we are analyzing it numerically. Because samples are getting constraints, and our expectation converges because we are now estimating the expectation of a transformed function given by our initial distribution function. So, in our case, samples are constrained between 0 and 1, but uncertainty less, and but going through those values, we have a convergence, increasing the number of samples, we get better and better uncertainty bounds. Moreover, we can observe how the histogram looks like, and we can see which where expected value is concentrated. And this, of course, does not look normal, because this distribution will not be normal. We've pushed the normal distribution through a logistic distribution, and it gives us the expected value, the biggest mass, somewhere around here. Look at that, it's not at the value of the mode. The expected value was about 0.7, the mode value is about 0.9. This is, of course, consistent with analytical computation, and that's generally the good part of what we are doing, as long as we are doing our sampling properly and the estimates exist. Then they are consistent with analytical computation, for example, of this analytical push-forward distribution. That is the distribution of values of normal numbers transformed by inverse logit distribution. But that is for very simple distributions. Normal distribution is relatively simple, because while formally normal distribution takes values that are real numbers, the practical numbers that happen are numbers that are between mean -3 and +3 standard deviation. That is a 99% confidence interval. So it calls 6 sigma, so 6 standard deviation from the mean from both sides. Going outside of that interval is probability 3 in a million. So that is a very, very low probability event, because normal distribution is relatively highly concentrated. This is not something that always happens. What happens in many cases, especially in case of real events, events with large variance, events involving people, events involving faults, we can have so-called heavy-tailed distribution. Heavy-tailed distributions are distributions, informally saying, that that can generate values that can be large, and moreover, getting those values is not terribly unlikely. And the most basic heavy-tailed distribution, at least a distribution that has a possibility of being heavy-tailed, is a student T probability density function. This function arises in certain statistical tests. This distribution arises in certain statistical tests regarding normal distribution, but it's also often used, for example, in so-called robust regression, because, which we'll talk about later, it is much more robust with respect to outlier values, because generally those heavy-tailed distributions say, okay, this is a possible that outlier will happen. Like, for example, a genius will pop up in a population which has a normally average IQ. This is possible. Under normal distribution, it is practically not possible. In case of heavy-tailed distribution, it's still not probable, but certainly much more likely. So, student distribution is generally it looks horribly complicated, but this is the generally scaling constant. V is called degrees of freedom, which is completely unintuitive, because this can be a real number, and while you can understand that something has 5 degrees of freedom, it can be hard to understand why it has a square root degrees of freedom. And those degrees of freedom come from so-called chi-squared test in classical statistics, and we will not be covering that. But it's still stuck that the parameter is called degrees of freedom. And as you can see, it's generally a function in the form of constant plus x squared up to a negative power. So something like 1 over something plus x squared. So this takes positive value. It's similar a bit into a Range function, a function that is centered around somewhere and has a bell shaped. So it's similar to Gaussian but has heavier tails. However, it should be noted that in this form, student t-distribution has certain dependence on the degrees of freedom. In particular, as long as degrees of freedom are greater than 1, then the expected value is 0. There is an option, of course, of scaling the student distribution or changing its central location. So that's not a problem. But like for most basic case, 0 is expected value. However, for number of degrees of freedom of 1 or less, the expected value is not defined. This integral does not converge. The same is with variance. As long as variance is greater than 2, the degrees of freedom is greater than 2, variance is given as this ratio of number of degrees of freedom divided by number of degrees of freedom minus 2. If degrees of freedom are between 1 and 2, including 2, the variance is infinite. So while there exists an expected value, the variance can be infinite. And finally, if degrees of freedom are less or equal than 1, there is also no variance, which of course is also consistent with lack of expectation. And case when we have 1 degrees of freedom is called so-called Cauchy distribution. And Cauchy distribution is a maybe not famous, but most widely used example of heavy-tailed distribution, which has practical applications, for example, as a prior of a distribution of certain parameters in Bayesian computation, when they are being used because it allows certain numerical computation. What is important? Analytical computation here is practically not possible. Only numerical can happen. And as we can see, what happens here? This is our standard estimator of the expected value. This estimator, that is an average of samples. As we can see, samples are coming, the estimator starts to converge, and then heavy tail drops an outlying sample, which completely jumps and changes the estimator value. And that will be happening. You get some convergence and then an outlier comes up. And so on and so on. And it can happen any moment. Even if we take 10,000 samples, we still won't have a convergence because the expected value does not exist. However, you should note one thing. This is something that we are not seeing actually, because what we see here is a finite sample behavior. The actual effect of not existing expectation would be visible in the infinite number of samples. Infinite number of samples will get a number. If that number is weird, well, we might skip and not investigate the fact that we assumed some value, expected value, which generally we are not allowed to take because it's the model that we have, from which we compute the expected value, will be able to generate much more varying samples. And what's worse, it might be correct. Certain events are highly varying, like stock markets, earthquakes, stuff like that. But does the central limit theorem even hold in this case? Well, we are basing our computation on the central limit theorem, and we want to analyze how it behaves. So we will focus now not on the estimator not on the actual expectation, but we will look at how the values of the estimator change under multiple samples. And using that, we can see that that we do not fulfill the requirement on the central limit theorem. The estimator of the expectation does not converge to the expected value because we do not have the required normal distribution for this estimator. So does it mean that we cannot do anything with the distribution of sampling habit distribution? No. Those distributions are very useful, and probabilities are well defined, and many expectations are well defined, just not the actual expected value of the distribution. For example, if we consider what is the probability of the -1, 0 interval, or otherwise, what is the we want to estimate the probability of function going through of samples coming from belonging in the -1, 0 interval. We do it by computing the expectation of the indicator function. And this is very well behaved. There are no weird jumps because, look at this way, we do not have a situation where we are adding this random number that can be large to our estimator. No, we are only computing the counts of our estimator. We are adding ones and zeros depending on if sample was in the interval or was not. So the samples that are very extremely out of the interval are indistinguishable for us from samples that are just beyond its border. So the indicator function is resistant to, doesn't have a problem with this abnormality of the distribution. And we can of course estimate those errors together with Monte Carlo standard error, because Monte Carlo standard error is also well defined, because in this case we are just averaging the values of the values of counts of behavior or the indicator of values of an indicator function. So still, samples from the nonlinear function for which we push the heavy-tail distribution are behaving very well. And even if the variance exists, even the expected value exists, it is still issues with using the estimator, because the variance of that estimator can be very jumpy, because it is not defined. So we will get convergence to the value of the mean, but we won't get good, reliable estimators of the of its variance. We won't get good error quantification. And analyzing the estimator behavior, which is again the error estimator should be normal if central limit theorem holds, then we don't have such situation. We'll have this that our mean estimator is very flat in the middle. So it is not normal, and estimating values that do not exist or do not have proper quantification are very difficult. However, if mean and variance are defined, the estimator behaves very reasonable, practically undistinguishable from the normal distribution estimator for normal distribution, which is actually very good, because with rising number of degrees of freedom at infinity, t-student distribution becomes a normal distribution. So students distribution is useful for situations which we want to add some heaviness to the tails of normal distribution but still keep its behavior. Cauchy distribution, so the case with 1 degree of freedom, which does not have a mean or variance, also is useful but for different applications. And of course, in case of student distribution, we can empirically confirm central limit theorem behavior because the error of the estimator will follow the normal distribution. So, what can we do? As I mentioned a moment ago, while the expectation does not exist, in our model we might not realize it. We might not realize it, and we'll just get a number. And that number, unfortunately, might lead us to wrong conclusions. So, is everything lost? No. We can use certain diagnostic tools that we can have. And one of the methods of analyzing is our distribution is heavy-tailed or not, is so-called analysis using the Pareto distribution. Pareto distribution is a specific distribution which is in which the probability of values follows so-called power law. So this is a function that is kth power 1 over kth power of z. So it behaves not as a number of it doesn't is not exponential like normal distribution. It's more heavy-tailed, and we use that in case of k equals 0. It reduces to the exponential distribution, but not normal, no square here, just exponential distribution. And this Pareto distribution can be used to determine if function if samples are coming from heavy-tailed distribution. We use actually tools from classical statistics, which we use as a test function. This is a point estimator of k hat. That is the estimator of the coefficient k of Pareto distribution. And the idea is that we take our distribution, we take most of it which is located close to the mean, and values that are far away from the computed mean, more than normal standard deviation that come from the sample, because remember, we can always compute the value of the estimators of mean and standard deviation. It is unfortunately the case that they sometimes might not make sense, which is again we are testing for its will be visible or not. And in this case, we split our distribution into the bulk and tails. So bulk values located near the mean, tails values located far away from the mean, and then we use for those values in both sides, left and right extremes, we use the so-called Zhang and Steven estimator of k hat, and we get its computation. Generally, as long as k hat is less than 1/4, everything is okay. This distribution, it can be negative, it can be 0. It is okay. We have no problem. Sampling will work and everything will estimate nicely. If k hat is greater than 0.7, then we have a problem, because that is heavy-tailed distributions for which our computation, especially of not protected by proper push-forward function, but just estimating the values of the distribution, expected value of the distribution, then might be issues. Values between 0.25 and 0.7 are difficult because we do not have a good rule for that. So they have to be investigated per case using different tools, making histograms of the estimator errors, etc. And for example, if we took our samples that we had before, what we can see? We can see that if we take our Cauchy distribution, so the first samples here, then we can see that, so we can take those values and compute the tails for them. Depending on the small samples, k is even larger. In case of the larger samples, it drops a bit, but still is well above 0.7. For student t distribution with 3 degrees of freedom, we have k hat close to 0, which is value that is completely acceptable and without any issues. In case of k hat, in case of student distribution which is with degrees of freedom greater than 1 but lower than 2, then we are in this problematic interval between 0.25 and 0.7 when we are not actually sure what we can do, but it's sketchy. And for normal distributions, k hat becomes negative, and that's generally makes the situation not problematic at all. The distribution is not heavy tail at all, and there will be no issues caused by that. So, what are our main takeaways from this part of lectures, the part from Friday and now? Monte Carlo sampling, as long as the distribution is not absolutely heavy-tailed, gives us good estimates and error quantification, and in case of heavy-tailed distribution, we still can do something using proper transformation of variables and formulating our goals that makes sense. For example, histogram for such distribution makes sense because it's a collection of indicator functions. What doesn't make sense, again, is the expected value. If we want to estimate probability, we should be aware that estimates of probability are always followed by their own error. This error is a Monte Carlo standard error that comes from central limit theorem when computing the relative push forwards. If our distribution is bad, difficult, does not have a quantity that we want to compute, and or the sampling procedure is not consistent, then we might have an issue. And this issue is problematic this way, that if we do not analyze what we want to do and what we are currently doing, we'll get a number. And this is something that happens to students many times. Number pops up, this is the result, we do not critically evaluate that. Results, especially in statistical sampling, need to be critically evaluated. Moreover, we can help a bit with heavy tail distribution using diagnostics of tail behavior like k-hat estimator, but that still always was easy and simple for the one-dimensional case. In multi-dimensional case, the problem is that finding a quantile function or its equivalent that will transform our distribution will be hard. Grid approximation won't work because of reasons I explained before on the Friday lecture, that there will be a lot of computation of values that do not contribute. We need to get samples from the typical set. And we do not have an easy way of sampling directly from any given multidimensional distribution, at least not using Monte Carlo method. We can, however, do so-called Markov chain Monte Carlo methods, which we cover in a second, but I need to have a brief break in order to get some water. I'll be back in 1 minute or two. Okay, I'm back. So we can move back to the issue that is at hand. So the problem of Markov chain Monte Carlo. Uh, a minute ago, we finalized the Monte Carlo computation. We know how it works. But the problem is, of course, how to get samples from a given distribution, especially a multidimensional one. So let's start. What is actually a Markov chain? So Markov chain is based on so-called a Markov transition distribution. So a probability that what is the assignment of probability, conditional probability of moving from point Q to point Q with Q prime. So what is the probability of going to Q prime from Q? So what is probability of Q prime? Conditional on Q. So using transition distribution, we can actually evaluate the probability of moving from one point to different points. So for example, in a very simple case, let us consider a two-dimensional space with a normal transition distribution. We assume that movement in we have points in two-dimensional, so Q with one upper index is the number of dimensions. So we assume that probability of movement in one axis is independent on movement in the other axis. This is a very simple case, but it's possible. So we assume that moving from first point in x variable dimension and in y dimension are governed by individual probabilities, and in our case those will be normal probability distributions of probability of moving from point q0 to point q1 with a standard deviation of sigma. So starting from point here, we have possible transitions that can happen here. Those possible transitions, of course, is the entire space, but for example, we can move to many of those points. Which point we will move depends on the probability. We have this distribution, and of course, let's say like a random number generator will go through. We'll get a sample from that distribution, and we'll move to the next point. And which point? Well, it depends on which point we were previously. So this is so-called a Markov transition, moving from initial point to a new point. So Markov chain wanders over the space from one point to another, and which point will be selected next is governed by probability. And when we move from the first point to a second point, so after the first transition, we again have a new set of possible transitions. And again, only one of those will be realized because Markov chain just follows. However, where it went was probabilistically chosen. Markov chain is an iteration of Markov transitions. So the chain will be sequence of points that come by transitioning from initial point to sequence of others governed by the proper probability. And these things we are calling Markov chain. Now a bit complication. Generally, we are interested with Markov chains that have something called a stationary distribution. The idea is that stationary, otherwise invariant distribution of the Markov chain is that distribution that is preserved under the probability distribution. So averaging over all possible values of Q prime will give us the probability of Q. So starting probability of q prime, averaging over of q prime, we'll get the same probability but of q. So we'll recover this probability by this integration. In practice, a well-behaved Markov transition distribution will admit a unique stationary distribution. And that is important for us because the Markov chain will wander over the probability space as long as we will let it. However, if this Markov chain is properly behaved, so it's as a stationary, it's ergodic and stuff like that, then the points from the Markov chain will be in the typical set of a Markov chain stationary distribution. At least most of them. That means that getting what we wanted from before, if we have samples from the typical set, then we can estimate appropriate values of the expectations of functions that we want, as long as they exist, with those samples, because those samples preserve all the necessary information. And so the idea is that Markov chain not only wanders mostly around the typical set, but also it converges to it. So initially, Markov chain will wander towards its typical set, and after some time, it will start walking around it and will stay in it. So the longer the Markov chain will walk around the typical set, the more, the longer we'll run, the more and more samples we'll get that come directly from the typical set. Which is a good property because typical set, as we remember, is something that we cannot practically compute. We cannot compute the typical set of a given distribution. And this is nice because Markov chain Monte Carlo estimator is something that is very similar to Monte Carlo estimator. That is, the average of samples that were obtained from the appropriate Markov chain that wanders around the typical set will be, as long as the Markov chain is irreducible, aperiodic, or otherwise known as recurrent, this will be asymptotically consistent. That is, as number of the length of the Markov chain grows, its average will tend to the expectation that we are interested in. So, why this is good? This is good because Markov chain Monte Carlo is not only method of computing things using randomization, it also shows us a way of getting proper samples that will work. And moreover, we do not need complicated quantile functions, which are not computable in most cases, and we do not have other problems with sampling from directly from the distribution, which is generally not possible. The only thing that we want is that our Markov chain would have a stationary distribution that is exactly the one that we want to analyze. So how behaves this Markov chain, at least in the ideal case? Well, in ideal case, we have a situation that our estimator initially is not very convergent. It do have some error at the start. However, when it starts moving around the typical set, we will get better and better representation of those samples. And the more samples we get, the smaller the error will be. Unfortunately, this is not as good as we would like, because typical set can not necessarily will be very regular. It even can be very irregular with, for example, sharp edges. And initially, Markov chain will be okay, we will get to the proper place and we'll walk around here. So, iterations of the Markov chain will rise into the proper direction. Unfortunately, in those difficult shapes, it might be difficult to find a transition that will move further along the typical set. It will stay in the typical set, but it will get stuck here. And we'll get something like this. So the samples, instead of wandering around the typical set, will get stuck somewhere here. And even if we will escape this choke point here, our estimate can be biased because we have a lot of samples here and we do not have other samples from the typical set. And that is a problem that needs some kind of quantization. So, because there are those issues, we cannot use directly Monte Carlo standard error. We need to have something that is called Markov chain Monte Carlo central limit theorem, or otherwise quantities regarding the estimation of the error. Generally, the idea that as long as we have proper sampling, the expected value of our estimator will be the expected value that we want to compute. However, we have something that is called, instead of Monte Carlo standard error, we have Markov chain Monte Carlo standard error, which is similar, but while in Monte Carlo method, we had n here, so number of samples. Depending on the number of samples, the more the samples, the lower error, always, as long as the assumptions of the theorem are fulfilled, or the quantity of interest exists. However, in case of Markov chain Monte Carlo, instead of n, we have something called ESS, that is effective sample size. And effective sample size is a measure of how the Markov chain is autocorrelated with itself. And it is given by n divided by certain sum of autocorrelation coefficients of the Markov chain. This is a proper autocorrelation. So as you can see here easily, those samples are highly autocorrelated. So there will be a lot of autocorrelations between those samples, which are dropped lower here and here, right? So that causes issue that this number will be big, and in consequence, effective sample size will be small, and if effective sample size is small, then unfortunately, the Markov chain Monte Carlo standard error will be big. Practically, we of course do not have the quantity of the comfort of computing expectations, analytical expectation and variances, so we have to estimate effective sample size using proper autocorrelation estimators, which are based on the proper sums here and divided by estimator of the variance of our function. And how we can understand the expected sample size, estimate that sample size, effective sample size. Sorry, if there are no autocorrelations, so all the samples are independent, then we get a Monte Carlo standard error. ESS will become n, and everybody is happy. That does not happen in practice, unfortunately. Even in case of if we had know the distribution quantum functions, the random numbers generated from the from the pseudo-random number generator will have some autocorrelation. It might be small, but there will be. And so in all cases, we almost always have some kind of effective sample size that is lower than n. As long as there are positive autocorrelations. Because the more, when we have a positive autocorrelation, then we will increase the Markov chain Monte Carlo standard error, because we will have the ESS will be smaller than n, sometimes even significantly smaller. There is a situation possible that will have a total negative autocorrelations, and this will potentially decrease the Markov chain Monte Carlo standard error below the Monte Carlo standard error. However, this is extremely random situation, and there is no systematic way to guarantee negative autocorrelations. So you cannot create a sample method that will work better in this case. So really we have an estimated central limit theorem, because we know that our Monte Carlo Markov chain Monte Carlo estimator has a normal distribution that is centered around the actual expectation with a standard deviation given by Markov chain Monte Carlo standard error, which is we can only estimate using estimators of variance and estimate of effective sample size. So, what is the practice? Practice is that we do not want these values. Those values do not come from the typical set. We want only values from the typical set, because that will get us lower biases in our computation. And how do we do it? We do so-called warm-up. That is, we start the Markov chain, and after some time we don't use samples received up to this moment anymore, and we consider only future samples for our computation. It was previously called a burn-in, that we burn all those old samples, but the idea now is that we want to be more inclusive, and the name warm-up, kind of like the algorithms or an engine warms up to work better, so it has a more positive connotation. So theoretically, of course, after we reach the phase of exploring typical set, we should drop earlier samples and skip all samples from there. Unfortunately, we do not know where the typical set is, so this doesn't happen. There are adaptive ideas that you can analyze what's going on with samples and kind of detect that, okay, we look like we are in the typical set. But usually we rely on heuristics. In most of practically used Markov chain Monte Carlo methods, you usually work with 1000 sample length of chains for estimating anything you want, and 1000 samples that are used in a warm-up period. So you sample Markov chains for given distribution with 2000 samples, and you drop the first half. That's a practice. Okay. This slide doesn't look that good. Okay. What's going on here? The idea is that something that we were walking around before. I won't be changing this slide, because with OBS it's just irritating, so I won't be doing that. It's not that relevant, really. The title to be readable. Generally, the problem that we haven't talked about yet is that, when Markov chain has a stationary distribution, then it explores its typical set. Great. How to guarantee that a Markov chain will have the stationary distribution that we want? Well, This actually is a solved problem. It is solved by a Metropolis-Hastings algorithm. Metropolis-Hastings algorithm is an algorithm that is considered one of the most important algorithms of the 20th century. It was developed in Los Alamos, and this Metropolis algorithm original, which was then updated by Hastings, was developed there. It's a classic result from theory of computation, and is an idea how to enforce the stationary distribution. The idea is that we cannot get samples from the distribution that we want. We know that because it's complicated. We can, however, evaluate its density function, or at least something proportional to the density function, and at a given point. So we can evaluate this function. We have more problems with doing so because we can evaluate value proportional to the probability density function that you want. Why proportional? Because we don't need the normalizing constant, and in Bayesian computation we always work on denominators. Numerators, sorry. On numerators we drop the denominator, that is the total probability. We can find easily a distribution that we will be able to generate samples from. For example, multivariate normal distribution is a distribution that we can easily generate samples from. And this will be called a proposal distribution. Proposal distribution is a distribution that we can generate samples, preferably from the same space, but with some probability that we do not care about. There is some kind of distribution. It's random with given distribution. We know its density. That's it. Usually normal. Then we start with a point and generate a proposal, that is a sample from this proposal distribution, a distribution that is easy to work with. Then we compute something called Metropolis-Hastings acceptance probability, which is the either one, if it's a minimal value, or the result of the following quotient. Proposal distribution from a new point to the previous point divided by proposal distribution of previous point to a new point. If those proposals are invariant or like stationary, this will be the same, exactly both sides. So that is the same and it can be cancelled. And value of the probability density function in the new one and in the old one. So generally, the probability of acceptance probability will be depending on what is the probability value of probability density value of that function. If that would be negligible, if we move towards the areas where the probability density function takes a larger values, then the acceptance of this value will be always greater than 1, so the transition probability will be 1. If proposal moves us away from the high probability area, so the pi of q prime is lower than pi of q, then we have a probability, not 0, unless here is 0, but it's not 0, there is some probability of moving away. And the idea is like this. We compute this acceptance probability and then we use a random number generator to accept value. If it goes above the acceptance probability, we accept. It's below this probability, we accept. So if it's 1, we always move. If it's above that, we don't move. So if it was moving to, it was less than 1, there is a probability that we will be still stay at this new point. So we either move to the new point with probability a q, or stay at the probability 1 minus a q prime q. And like as I mentioned before, this is always usually normal. And if it's normal, then this is much easier to compute. But this is called a random walk metropolis algorithm. So let's do some examples. If there are any questions from this one person that is watching, do not hesitate to write in chat. Let's start with a normal example. This normal example is that we have we have a diagonal covariance matrix. We have a mean at 1 minus 1. Looks like this. So it's a probability distribution that is centered around point minus 1, 1 with perfect wheels as its contour plots. If we start sampling values from our distribution, we can see that after some time we will get samples that are centered around certain values. If we do multiple chains, we can see that the behavior is consistent. So starting from different points, those chains behave properly. And give me a second, I think that some figure has not compiled. Maybe it will be easier to show it, or maybe not. No, okay. So generally, doing chains, we move towards this point 1 minus 1. Moving multiple chains, we will get to those points. Those chains should get to the right point. Why? Because independent on the starting point of the Markov chain, the chain should converge to the typical set and explore it. We want to do some diagnostics of those chains because if it's a very simple problem, we can observe the chain and we can, for example, see issues as here, right? If there are multiple chains, and multidimensional space, that might be very difficult. Because even if something is biased, that bias might not be visible in individual plots of each variable. So we want to get some kind of metric to compute what we want to know. And there are two important values: within chain variance and between chain variance. The idea is that how much given chain is varying by itself and what is the differences between chains of each chain themselves. And that can be used in order to check if sampling is proper, if Markov chains are behaving properly. And this for this we use a statistics called potential scale reduction factor, which is called everywhere as R hat. Even in literature, everyone calls it R hat. No one used potential scale reduction factor. Generally, R hat is 1 if within chain variance and between chain variance are equal. Because if those variances are equal, then we see that all those chains explore the typical set properly. However, if there are some differences, R hat will either grow or diminish. Usually, it will happen that between chain variance will be larger than within chain variance. That will be a problematic situation, which will result in the growth of R hat. And it comes from the situation that one of the chains will get stuck in some kind of curvature trap in the probability density space, and others will explore properly. Or in even worst case, each of those will get stuck in different places. Second estimator is so-called Dewey statistic, which is the idea of splitting the chain into parts and checking if the first part and the second part of the chain behave properly, the same like previously. So we kind of compute the difference between estimators divided by some square of sum of their standard errors. Function that works currently and mostly used is so-called split RHAT, which is let's say best of both worlds, which is a so-called split potential scale reduction factor, or split RHAT. And idea is like this. We use multiple Markov chains for sampling of our probability distribution, which we generated using Metropolis Hastings algorithms. Usually, traditionally, we use 4. We use 4 because in most cases, in recent memory, we have 4 cores in our processors. So using 4 or 8 cores, and using 4 cores seemed like an efficient usage of resources. Now we can run more, however, practice shows that there is no benefit going higher. Because if it breaks, it will break, if it will work, it will work. There is no middle ground that having 20 chains will get, in general case, any good situation. Perhaps there are specialized situations that you really want to have a lot of Markov chains, but there are very specific cases. So we get our 4 chains after warm-up. Each of those have 4,000 samples. Idea of splitter hat is to cut each of those in half. So we will have now 8 shorter Markov chains, and we compute R hat for all of those. And in this case, we get the inconsistency both between the Markov chains and within each Markov chain individually, because any change there will result in the increase in R hat. Practical implementations of R hat now also modify it a bit, that it uses certain rank statistics because it provides more robust, but I would refer you to for example, stand documentation or papers by Andrew Gell-Mann and Michael Betancourt. So computing something with so analyzing what we had with our sampling, we had mean of each of, we can compute the mean and standard deviation of each of our samples, which are consistent with the set that we wanted. We computed Markov chain standard errors of those means. We computed an estimated effective sample size, which, as you can see, is lower than 1,000, which we had 1,000 of samples. And for those two, we can see an average acceptance probability of moving. So the average acceptance probability was of each step was 0.42, which is given standard deviation. R hat here, it doesn't make sense, but it was computed anyway. For variable 1 and variable 2, R hat is approximately 1, which we can accept as okay value. Really rounding to 2 or 3 points after dot will be absolutely efficient. If we increase number of samples to 5,000, we get similar results. Even relatively small effective sample size, better estimates of smaller Markov chain standard errors by 1%, and we get a bit better results with similar levels of R hat. And we can see how it converges to the values that we wanted, 1 and -1, with proper sampling, and we can see its distribution into the space. But let's take a more complicated example. And I think that complicated example can wait till Friday. On Friday we will finish the not Friday, sorry, on Wednesday. Wednesday, which is Friday, which will be again a remote lecture. We'll continue with Markov chain Monte Carlo with complicated geometry examples, which look like this. Spoiler. And we will cover also the practical current methods, that is Hamiltonian Monte Carlo. Thank you very much to all of you 4 people that came till the end. I am very happy to meet you, to see you all at this nice late hour. It's only 2 of you now. If someone wants to say hello on chat or ask any question, you're welcome to. If not, we'll be finishing in a moment. Okay, I see no questions, so thank you very much and have a nice day or nice night.